Good afternoon, everyone, and welcome to this second session in the afternoon in the Red Room. I'm Jeff Kennedy from the University of Auckland, and I'm pleased to be your chair today. This session is from Andrew Underwood, who leads the Dell EMC High Performance Computing and Machine Learning Solutions in Australia and New Zealand. He's a passionate innovator and seems to be a really solid, good person. So please welcome Andrew up to the stage.
Cool, thank you. Hi everybody, so Andrew Underwood from Dell EMC. For those that don't know who Dell EMC is, we're a new entity that's come together as formerly you may have known the EMC business, which has been a very large, world's largest storage provider over the last 30 years, and Dell, who was both a server, networking and infrastructure provider, and very well known for its laptops and PCs and end user, and recently we've come together as a new brand called Dell Technologies, and Dell EMC is the enterprise division of Dell Technologies, as well as a number of other companies that form part of Dell Technologies, such as VMware as well. So lots of partner and sister divisions as part of this. And at Dell EMC, our goal set forward from our founder and CEO, Michael Dell, is really to create technologies that drive and empower human progress. So I work in the high performance computing and machine learning division at Dell EMC, looking after the Australian New Zealand business, and really my team and my goal is to work with researchers, work with e-research leaders and IT staff, both in academia, in government and the enterprise space, to help them accelerate research and development, really increase their economic competitiveness. So to jump right into it, just quick a show of hands. Does anybody know who this lovely lady on the screen is? Quick show of hands. Everybody knows who it is. So Ellen DeGeneres, famous talk show host, comedian. But does anybody, who thinks that they can name all of the people in this slide? Anybody? I want to see if anybody likes to read Who Weekly or anything like that on the flights over. No? Nobody? This is actually, does anybody know what picture this is? Yep. So it's taken at the... so the award shows, and it's actually what's deemed as the world's most famous selfie. So this was a selfie that is the world's most famous selfie. The reason it was deemed that is because it was taken by Ellen DeGeneres and Bradley Cooper down the front, actually holding the camera. But it contains what is deemed the world's most iconic and famous celebrities of the 21st century or today. And yet, these are the most famous celebrities of today, and most people can't actually name them, which is a little bit unique, but probably not so much in this space where people may not be as interested in this. But the reality is that the reason I show you this is the world's most famous selfie, and yet at a place where you'd think that most people would be able to identify all people in the selfie, a researcher at a university in New York decided to go around campus, and over the course of a day, he asked around 300 students if they could identify who these people were in this selfie. And on average, across those 300 people that were asked, or 300 groups of people that were asked, on average it took over 3 minutes for them to correctly identify every single person in this selfie. I'm not going to try and name them all, but the reality is that that same researcher at that university decided to take the footage of the red carpet award ceremony and feed that footage and the audio and the visual from that footage through an algorithm that they built for machine learning that would then teach itself to identify based on who the reporters were naming, the names that were mentioned as these people, and their faces came up on the video. And that machine learning algorithm then trained itself on who these people are, but not just these people and all the other people on the red carpet. He then showed that this same photo and a number of other selfies that were taken at that time, showed that selfie or fed it through the machine learning algorithm, and it took 0.1 of a microsecond to identify and correctly label with 99.9% probability every single person with the green box around their face. So 0.1 of a microsecond, as opposed to all of the 350 groups of students, target demographic for the world's most famous selfie, which took them, numerous minutes. And a lot of them actually, when you actually read through how long, the vast majority of people got to over 10 minutes and walked away and gave up. So the point of this is that in the past, when we wanted a computer to do something new, we had to program it. Whereas now, we're able to teach these computers based on feeding them data. And this is really driven by a new term and a new technology of deep learning. And this is the same technology that's powering our social media devices, internet activities, and internet access so that we can have better user experiences and, whoop, my slides are jumping, sorry, but more of a interactive experience with our data when we're online. So deep learning is very straightforward. It's a branch of artificial intelligence. A branch of artificial intelligence which uses data to learn and evolve. The more data that we feed into these deep learning or machine learning algorithms, these software algorithms, the more intelligent and more empowered or more cognitive than they can actually become. And the reality is that in our everyday life, we all have access to data. We all learn from data. We all ask questions of that data, and then we make predictions and decisions on that data. So if you're like me and you're pretty horrible at sports, every now and then a group of friends will call me up and they say, hey, do you want to go 10-pin bowling? Typically, I'll pick up that bowling ball and I'll think, you know, I am the gift at bowling. I'll go down that lane and I'll throw the ball. It'll get halfway down the lane and it just goes straight off to the gutter. Horrible, 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 embarrassing. But the reality is, before I pick up that ball again, I will think about what just happened, my interaction. I'll think about my past experiences when I've thrown the ball in the past, when I've attempted to bowl, and I will think, did I throw it too far? Did I throw it too hard? Did I throw it too short? You know, do I need to put more of a spin on it? Do I need to change my hands? And the reality is that then I will learn from my past experiences, just like we do in everyday life, and then I'll make a next decision. And hopefully, if you're nothing like me, your next decision will be to throw it a little bit better and actually get yourself a spare or knock down a pin. So just like in everyday life where we use and learn from data and we think about data, computers, the more data that we feed them, can use complex algorithms to train and label their experiences to help us, or ideally help themselves, to make better predictions based on data. So the reality of deep learning is that it's actually about probability without human interaction. Deep learning is based on these complex neural networks or deep neural networks. Sometimes you'll hear these terms called artificial neural networks or deep neural networks, which are based on the biological makeup of our human brain. And effectively, the deep neural network is called deep because a computer algorithm is able to label data in such a way that the more that it breaks down this data, the more depth and layers that it can find within data, then the deeper it becomes. So when you think of an object or an image, if you think of a human face, what you can see here, hopefully from the picture on the screen, is that there are hidden layers within that data that a human won't necessarily think of when it first sees another person's another person's face. However, we know that there are these hidden layers within our brain, that the synapses within our brain, or what is in deep learning called the neural network, the synapses will start to fire. They will start to connect pieces of data together, and they will start to put together and say, yes, that face is from Andrew Underwood. I've seen him bowl. It was very horrible at 10-pin bowling, and I know who that person is. So our brain breaks down and starts to label data. So researchers have been working on this way to effectively label and discover hidden layers within data, and then build these complex neural networks that are based on the parallelization of the human brain. The human brain does not do tasks in serial. When we think that we are doing a task in serial, like picking up a water bottle, the human brain is actually doing all these other tasks in parallel to ensure that, that we can complete the action that we set out to do. And so the advantage of the technical, I guess, architecture of a deep neural network is that it's able to undertake all of these complex tasks of finding, identifying, and labeling, and then correlating hidden layers in data in parallel, so that as a computer or a machine does something, the probability of, or the action is done without human interaction or human action. So when we think of things like self-driving cars, or a bionic eye, for example, one of the reasons that deep learning has to be done in parallel is because if you think of the interaction of a bionic eye, if you were able to create a bionic eye, and a person who's blind was to use that bionic eye, all of the data ingestion and the probability that is fed back to that person's brain through the bionic eye needs to be done in parallel, extremely fast. And the reason for that is that we can't have the person with the bionic eye take a step and then all of these serial tasks to process the data and feed it to the brain need to be done and then need to be processed, and then the person can take another step. They need to be able to do all of this relatively fast, or as fast as somebody who does not have a bionic eye is able to ingest and label or make a decision based on that data. And deep learning itself is not actually the new kid on the block. Deep learning has been around since 1943, and a lot of people think that it's quite a common and quite a new field of research. But back in 1943, there was an invention or a system called threshold logic. And threshold logic was the start or the concept of, what probability and what logic in order to define an outcome. Then in 1958, perception was built. Perception was actually a new generation of what we now call a high-performance computer or a supercomputer that was specifically designed to help people make decisions or decide on probability just by using human chess. And now right through from 1958 right through to the start around 1999, there were numerous different research topics around artificial intelligence and deep learning and machine learning and building supercomputers to label data, make decisions on data without human interaction, both in the form of computers that can play chess through to computers that can play poker. Now, the whole point of training these computers to play poker and to play chess is that then they can start to do things like bluff, make decisions multiple steps ahead of the data that's being fed to them at that one point in time. So it's all about making decisions in parallel and making more and more decisions in parallel. Then in 1999, it really took off, this deep learning really took off because of the big web tech boom in the United States. With companies such as Google, for example, using GPUs, graphical processing units, inside of their compute servers or their server farms in order to take advantage of the thousands of cores that exist within a graphics card to make and process data in parallel. These companies, like Google, for example, now use deep learning in their Google images and their search terms, so that when you type something into Google, all of this processing that's done and all of this text prediction and all of the labeling of data as they crawl the internet to label data is able to be done in parallel in a very fast manner to feed data back to the human being without a programmer actually going through and manually labeling the data. So these computer algorithms are able to do this themselves. And now in around 2012, or 2009, there were many benchmarks created for this new field of deep learning that really set the bar and set the direction of where or how researchers and how computer programmers are able to take advantage of this field of deep learning in a very simplified manner. And that came with the creation of many open source algorithms that we use today. But there are really three ingredients to this deep learning or artificial intelligence. The first is that you need large volumes of data. So when you think of the term big data, we're talking about huge amounts of data. You can't. During the U.S. federal election, there were many people that were saying our AI algorithm has actually predicted that X is going to win the U.S. election. And the reality is that an artificial intelligence algorithm it's very unlikely that it will ever be able to predict an election. Why? Because those two candidates had never gone up for an election before, and they were both campaigning on different issues that that other candidates hadn't gone to an election before. So there was not a huge amount of data for their AI algorithms to actually become a deep learning algorithm. It was more just an analytics database that was saying, this is what we think is going to happen. So the reality is, in order to have an artificial intelligence system, you need huge amounts of data. You also need these software algorithms that can self-label and self-label data, be that data audio, images, or text. And then with this huge quantity of data, you need the ability to do parallel processing. So one of the things that's boomed this, as I said, around 1999, was the uptake of GPUs, or graphical processing units, within compute servers. Now, a traditional CPU has anywhere between, well, theoretically 1 core, but most are 2, up to about 22 cores that can process tasks in serial. Graphics cards, or these GPUs, are designed with thousands of cores. Some graphics cards have around 2,500 cores that can process tasks in parallel. So the ability to process in parallel has really been the third and final ingredient that's driven deep learning and artificial intelligence in the enterprise and academia today. And as I said, that second ingredient is the framework. Most importantly is that because the whole concept of deep learning and AI is to have computers that are able to learn from data, the more data they ingest, without having somebody actually program the software itself or write the code from scratch and do the manual labeling, there needs to be these frameworks. And the open source community and the web tech community has actually driven this second ingredient. Microsoft, of all places, has been one of the biggest partners to actually fuel that second ingredient. And so we've been doing a lot of work with Microsoft. Their ingredient is Microsoft Cognitive Computing Toolkit, CNTK it was formerly known as. And their Cognitive Computing Toolkit is actually what they've used to power lots of the devices on their Azure cloud. So you think of things like Microsoft Bing Search. When you do image labeling through their image service, or video search, how does it know that that video is what you searched for without somebody manually labeling those videos? Because they're able to run through the frames of the video, but they know what the image relates to, so then they can automatically label it themselves. As well as Cortana. Are people familiar with Cortana? It's effectively Microsoft's version of Siri. If you have like a Windows 10 laptop, there's a Cortana application. You can speak to Cortana using audio, and it will translate your audio into text and then use that text on the internet to actually search for what you're looking to do. Or it will take that audio and then do an action on your computer. So a good example is that if you want to set an appointment with Cortana, you can click a button on your laptop, and you can say, Cortana, create a meeting appointment for 7 o'clock at this restaurant, and it will actually translate the audio in your voice into an actual action based on all of the audio that it's heard from millions of other people who use Cortana. So it hasn't been trained specifically on my voice, on my accent, or how I talk and the language that I use. It's trained on millions of other people who are interacting with Cortana and labeling certain accents, background noises, knowing how to filter them out, and it's teaching itself the difference based on mistakes and probabilities and actions that those users make, and the feedback from users who use Cortana. So Microsoft has used their cognitive computing toolkit to really take advantage of interactions on the internet, through Cortana on the desktop through to their Bing search. And now they've made open source their cognitive computing toolkit so that people and researchers can effectively create their own deep learning or artificial intelligence systems based on their own data. So we've been working in our HPC labs to actually take these frameworks and optimize them and speed them up for our platform, for what we call our HPC system for research. And what you can see here is that traditionally, this is actually some benchmarks of some of the other common deep learning frameworks. So people may have heard of things like Theano, TensorFlow. TensorFlow's from Google. They've also open sourced their technology. Torch 7 and Caffe. Caffe is what Facebook use. And you can start to see that there are limitations in the ability for these to scale when processing the amount of, or learning from images per second. So you can see from here, using two of our compute platforms for machine learning, what we call our PowerEdge servers for HPC, with 8 graphical processing units, or GPUs, we're able to learn from 70,000 images a second. So we can actually learn or process 70,000 images a second. Those image qualities are quite high quality as well, ranging from 2 to 4K images off of video feeds, off of surveillance systems, etc. We're able to process all of this and then label that data as well with an accuracy above 99.9%. And that's the critical part here, is that by ingesting data into our platform, we can learn from we can teach a machine at 70,000 images per second. Whereas the other frameworks really haven't been optimized to scale. So they're still quite isolated in the fact that they don't scale outside of multiple compute servers. The other advantage that we found with CNTK is that we can optimize it to run on both a workstation under a researcher's desk, through to a supercomputer in a university data center, and then have the ability for those people to burst to the Microsoft Azure cloud and use that as well. So flexible delivery options was another key thing for us. And then this is just an example of that system that we've built and designed in order to take advantage of this. This is what we call our HPC system for research. It's both compute, networking, storage pulled together in order to learn from data and help researchers actually train data. But the system also deploys the other packages and other common deep learning algorithms for researchers to take advantage of. And this is just an example of the graphical user interface that researchers can access in order to understand data, data probability, prediction, etc. I'm going to skip through this one. But what we also did, and this is probably the more interesting part, is that we partnered with a long-term customer of Dell, which is called CASIA, or the Chinese Academy of Science Institute of Automation. So has anybody heard or familiar with CASIA in the past? CASIA is actually one of the world's leading machine learning and artificial intelligence organizations globally. They're listed as one of the top 10 in the world for machine learning, and they're a division of the Chinese government's effectively academic research arm, but they do a lot of industry application. So we partnered with them to build a system that will help Chinese researchers to take advantage of artificial intelligence. This system is called Zhige, and Zhige is a complete graphical user interface accessible via the web from researchers right throughout China who are able to then access it to take advantage of the infrastructure and all of the algorithms through one place. Zhige does things like image classification. So it's able to process over 1 billion images per second and classify those images for probability prediction for researchers. It also does speech recognition as well, translation from Mandarin and Cantonese to English and other languages, so that as researchers and patients within hospitals, for example, a good application of the speech recognition was that a hospital where we'd actually rolled this out to had admitted a patient who was actually hit by a car in China, unfortunately, a tourist who didn't speak Mandarin. And so the doctor was having quite a difficult time working with that patient to help calm him down. Using the speech recognition app on the doctor's phone, this is no joke, he was actually able to start to help to translate into English so that the tourist was able to calm down and relax a bit more. So multiple different fields of application. It was actually the purpose of the doctor having the speech recognition app was because the doctor was also a professor at one of the local universities and was testing it himself, but then decided to use it to sit in a human setting to test it out. And we also do text classification. So Zhige is doing text classification where researchers have been able to take advantage of it to do sentiment analysis. And a really good example was that they were doing sentiment analysis on an online transaction store. And funny enough, they found that they were trying to understand sentiment of people who left reviews in English. And they actually found that if an English review on the store was 5 out of 5 stars, yet it had a question mark, there was a 99% chance that that review would actually be a negative review and should be converted to a 1-star review. And the reason for that was that Zhiger did text analysis on teenagers who spoke English in China and worked out that the only reason that they would be leaving a question mark was that they were asking a question like, who would use this? Why would you buy such a thing? Does anybody see a need for this? And the researchers were actually able to identify through sentiment analysis that there were certain things in English language that did not translate to Chinese language. And then we've also got light GBM. So we've also built in a package to our HPC system for research where people are able to do graph analytics using the same platform, the same infrastructure to do things like, if you can see from this example, we're able to ingest images from X-ray machines, and then within 53 minutes we're able to train all of the machine on all of labeling the data for what does cancer and what a healthy X-ray looks like, or in this case it was actually what we used in our proof of concept was a mammogram, labeling the mammograms for what's safe and what's not, and then with light GBM we're able to actually pre-process all of the patients that had been gone through the doctor or a hospital in a week, and then we're able to go back to that doctor the next day and say, you did a 12-hour shift yesterday and we've pre-processed all of your patients' mammograms, and we think that these two you should just double check. And it was because we found that doctors were asked to work longer hours. They were rushing some patients through because they were stressed and they were tired. So this system didn't replace the doctor, and instead what Zhiger did was it provided a secondary line of quality assurance to the doctor, so that the doctor could go back the next day and before he told his patient it's all clear, go back and double check the mammogram. And what we find with Zhiger is that, and with all deep learning and artificial intelligence, is that if you've got enough data and you can label it and train it, then it can be applied to audio, image, and text as well. And so that's where we're going at Dell EMC, is working with researchers, not just through the Zhiger example, but we're also working with researchers right across Australia and New Zealand in a number of industry-based research agencies in New Zealand and Australia, as well as universities, to help them to apply deep learning to these, to image, audio, and text as well. And through our work with Zhiger as well, we also were last year at the China Supercomputing Conference, or the China HPC Conference, we were awarded the top award for the conference, which is their Artificial Intelligence Award for applying technology and research to actual industry-based outcomes. And a lot of this, just to wrap it up, a lot of this and a lot of what we've been doing with Zhiger and other customers in Australia and New Zealand is stemming from our goal as an organisation. And there's a quote from Michael Dell here that he listed at CERN. And really, he says that our goal is to put the tools in the hands of the people who are going to solve the world's biggest problems. And that's our goal at Dell EMC. Our vision is to drive human progress, and our goal is to put those tools in the hands of the people who are going to solve the world's biggest problem. In order to do that, and for us to do that efficiently, we have to make sure that technology is accessible, seamlessly adoptable, and secure. So by building all of these platforms and all of our learnings with Zhiger and other customers throughout the world, we've applied that to our HPC system for research so that other customers can take this platform and apply it to their research without having to spend weeks or months trying to adopt new and emerging technology. So I think that's it, but thank you very much for listening and for your time.